All right, so welcome back. This is section 11.2. This section is about applications of trees, and there's a lot of cool stuff in this section, but I have decided to make most of it optional and focus our attention specifically on one application, and that is binary search trees. So a binary search tree is an ordered, rooted binary tree, which was all defined in the previous section, where each vertex is given a value called a key, and it's sort of like usually going to be like an element from a set that is being stored at that location in the structure, and these values, the keys, have to follow the rule, and the rule, which I'm going to refer to as the star rule just for this lesson, is that the value of the left child must be less than the value of the self, like the vertex itself, which in turn must be less than the value of the right child. So left less than self less than right child. That's going to be our rule. So, as an example, suppose we have a data set. Now, for this data set, I've just got a bunch of numbers. Now, they're in a list, so this is like my. You can think of this as an array. If you're programming, you would you input this array, and we're gonna go through this array in order, so you could iterate through this thing, and we're going to take these elements and put them into a binary search tree structure. Now, the reason we'd want to do that. We'll get to this in a second here. The reason we'd want to do that is because we might want to store this data in a way that it can be quickly retrieved. So if you just have the data stored in an array, if you want to search through that structure and find a particular element, if you want to find like the element 3, and it's just in this array somewhere, then you really the only way to search, well, that's not true. There's lots of different ways to search an array, but the most common way is to do a linear search where you start at one end and you just say, is that 3? No. Is that 3? No. Is that 3? No. Is that 3? No. Is that 3? And you just keep on going until you get, hey, is that 3? Oh, yes, it is. And then you would return probably the location of 3 in that array. But that's pretty slow, right? Because if you're searching for something that happens to be near the end, it would take a lot of steps to find that thing. So a binary search tree is a more efficient structure for storing and quickly retrieving elements from that array or from that set. So in order to construct our binary search tree, we're going to do the following algorithm. For each element in our list, we're going to, starting at the root of our tree, we're going to follow the star rule that left value is less than the value of the vertex itself, which in turn is less than the right child value. So following that star rule until we find an empty spot. And then when we find that empty spot, we'll insert our element. So our tree starts off being empty. We haven't inserted any of the elements into the tree. So the very first time we apply this rule, we take the first element, 4, and starting at the root, we say, oh, that is an empty spot. So we're going to insert 4 at the root. Okay, first element ends up being the root. So now that is going to have a left child and a right child because this is a binary tree and it's ordered left and right. So then we take our next element, 7. And we have to follow the rule that the left child must be less than 4 and the right child must be greater than 4. So if we want to insert 7, it's got to go to the right of the root. So I'm going to put 7 in over there. Now 7 will have a left child and a right child. All right, time to insert 5. So now I take 5 and I want to come over here and say, it can't be to the left of the root because it's not less than 4, so it's got to be to the right. But that spot is already filled up, so I've got 7 over there. But now 5 is less than 7, so that means I've got to put 5 on the left, in the left child of 7. So 5 has got to go there. And then that's going to have a left and a right child. All right, 2 is less than 4, and that spot is empty, so we put it in there. Left and right child. 8, greater than 4, also greater than 7. That spot is empty, so we put 8 in right over there. 1, less than 4, right? So we go to the left. We already have a 2 there, and 1 is less than 2, so we go to the left, and we find an empty spot, so we insert 1. 3, less than 4, but greater than 2, so we insert it here. 9, greater than 4, greater than 7, greater than 8. So we're going to insert 9 down there. And then finally 6 is greater than 4, but less than 7, so we go to the left. We find 5. 6 is greater than 5, so we go to the right. And we insert our 6 right there. Now, when you insert something, you say, well, okay, it's going to have a left and a right child. But now that I've inserted all of the elements into my structure, into my tree structure, all of these empty spots at the bottom, you could have all of these point to empty places. Like that would be like if you were using classes, it would be like they're all pointing to null or something. But I'm just going to erase them for the sake of analyzing this tree that we built. Okay, so let's just look at the vertices in this tree that are actually assigned some values. Okay, so there we go. This is a binary search tree, and having followed this rule, it results in a situation where if you take any vertex and look at the left subtree and the right subtree, all of the elements in the left subtree will be less than that vertex, and all of the elements in the right subtree will be greater than that vertex. And you can do that at any point in the tree. So in particular, starting from the root, all of the vertices, all of the values in the left subtree, which is the subtree formed by the left child of that root, those are all less than 4. And all of the vertices in the one on the right are going to be greater than 4. This means that if you're searching for 6, for example, then all you need to do is make a sequence of decisions, a sequence of comparisons and decisions. Are you going to go to the left or the right, left or the right, left or the right? And so we can find 6 very quickly by just saying 6 is greater than 4, so go right. 6 is less than 7, so go left. 6 is greater than 5, so go right. And then you found it. And that was just 3 comparisons. The maximum number of comparisons you could need to make is equal to the height of the tree. So max number of comparisons required to locate an element. Locate element equals height of tree. And having a balanced tree is valuable in a situation like this because a balanced tree is usually going to be sort of a minimal height. If you have an unbalanced tree, then you might end up with something which is much higher, a tree which is much higher than it needs to be. So, for example, if we had ended up with just putting all of these, if these were going in order, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, like that, then we would have just done 1, 2, 3, 4, 5, 6, 7, 8, 9, and we would have had 9 levels and a height 9 tree. That is no more efficient than just an array. So that's kind of boring. In fact, it's pretty much identical to an array. It's just like a linked list. But in order to get this tree structure, it's kind of valuable that the initial data set be randomized. So having this randomized means we're more likely to get a balanced tree with sort of a minimal height. And if you don't have a balanced tree, it is possible to sort of write a program that will take this structure and balance it. That may be an assignment that you're given if you're taking fundamentals 2. And actually, I have been in touch recently with your professor Shefali Lenore, I believe. And she and I have spoken about this subject, and so if you are in Fundamentals 2 right now, then you're going to be studying this possibly right now. I think maybe in the same week that we're doing trees, and in that class you are going to be going into much greater detail with this subject, learning how to write algorithms to insert and find elements in this type of data structure, as well as potentially balance the tree or split it into subtrees or whatever. So there's been a fair amount of vocabulary in this lesson, which is kind of specialized. And if you don't have a lot of programming background, don't worry about that too much. My main focus here is for you to understand this rule, all right, the star rule up here, and how to use that to take a data set and form a binary search tree out of that data set. Okay. So this process that I've demonstrated here is what I expect you to be able to do. There is one more thing I wanted to say about this, and that is if this tree is balanced over here, then the number, like the height of the tree, which in this case is 3, should be approximately around log base 2 of the number of vertices. It's, I think, the floor of log base 2 of n, where n is the number of vertices. And that then is also the number of comparisons, so the number of steps essentially needed to find an element in this structure. So when you're comparing different search algorithms for different data structures, sometimes you want to compare, well, how fast are they? Like, what's the maximum number of, or the average, in some cases, number of operations, steps that would be required to find something in that structure, to like retrieve something from it. And for this type of binary search tree, that's called the complexity, and for this tree, it's log n. So, just wanted to mention that. Okay, cool. I think that's good. It might have been a little longer than necessary, but we'll go for it.